Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for those in differential calculus heading into integral calculus. This topic is indefinite integrals, which is not like definite integrals. They're actually honestly very closely related, obviously, because they share some of the same name. But definite integrals are integrals, basically we think of them as areas underneath curves, right? So if I gave you a definite integral, let's say the integral from a to b of f of x dx, you would think of that, or should think of that, as the area between the function f and the positive x-axis, or I should say the x-axis, from a to b. That area could be negative, so it's a signed area, but that's how you would think about a definite integral. However, an indefinite integral, well, that is created just so that we have a better notation for what we call the antiderivative. By definition, the notation without the integral sign, without upper or lower limits, is actually an indefinite integral, and it's a shorthand notation for the antiderivative of f. And so when you see the indefinite integral, in other words, the integration sign without limits, that just means I want to know what I would take the derivative of to arrive at this function right here. So it just returns the antiderivative. However, remember, antiderivatives have that plus c on there because, well, your antiderivatives actually creates a family of solutions, or a family of antiderivatives, mainly because if you took the derivative with respect to x of capital F of x plus a constant, if capital F is an antiderivative of little f, then the derivative of capital F would become little f, and the derivative of a constant is 0, and so this is little f of x. So now we're going to go ahead and use this definition in all the problems in this video series. I should mention though that this video specifically is just an introduction to indefinite integrals and their properties. So we're not going to actually evaluate any in this video. We're just going to align our brains with their properties, right? So here we go. The properties of indefinite integrals really mimic the properties of definite integrals, or some properties of definite integrals, where with a definite integral, if this is an integral from, let's say, a to b, you would be able to factor out a constant out of that. And that's exactly the same with indefinite integrals. Also, if it were a definite integral from a finite number a to a finite number b of the sum or difference of functions, you could break that into the sum or difference of the definite integrals. Well, the same thing is true for indefinite integrals, integrals without limits. The key thing to remember here is that the indefinite integral returns the antiderivative. So if I had something like the integral of 5 times, let's just make up an antiderivative, or a function that we know the antiderivative for, let's just say x squared, okay, dx. That would be 5 times the indefinite integral of x squared dx, and then the antiderivative of x squared is x cubed over 3. And then we would say plus some constant c. Well, that constant c, because that's what we call the constant of integration, that constant c I'm going to call actually c sub 1. And the reason why I'm doing that is you're going to distribute this 5 to each of these two terms, and you'll get 5/3 x cubed plus 5 times c sub 1. But nobody wants to see a constant times a constant, especially when that constant is going to be arbitrary. So we're going to bleed those two into one another, and we're going to call that c, not c sub 1, but c. So 5/3 x cubed plus c is the antiderivative, or the indefinite integral of 5x squared. So this is using the first property as far as being able to pull the constant out in front of the indefinite integral. And then I just wanted to showcase that when you find the antiderivative for that function x squared, you do have that plus constant. And when you distribute that 5 through, you can actually just call that constant a different c. And I like to use c. In fact, most of us do. So we go ahead and call the first constant c sub 1, so we can reserve c for when we multiply that constant by 5. Honestly, you'll rarely even think about it. You'll automatically do it. So it's not that big of a deal. Now at this point in a textbook, you'll have a whole table of indefinite integrals. However, I pretty much think that most students should know antiderivatives already. So I'm only listing out the biggies, the heavy hitters. And so the ones that you'll see very often in Calc 2 are the indefinite integral of secant squared. That will turn into obviously the tangent, because the derivative of the tangent is the secant squared. And then don't forget there's a plus c. The indefinite integral of 1 over 1 plus x squared is probably one of the most important indefinite integrals that you're going to deal with in Calc 2. And the antiderivative of 1 over 1 plus x squared is the arctangent of x, or the tangent inverse of x. That is because, again, the derivative of the tangent inverse is this guy right here. And don't forget, when you integrate 1 over 1 plus x squared, you get that tangent inverse of x plus a constant c, arbitrary constant. The next one that is super duper important, the integral of 1 over x. Now, a lot of people really screw this one up. It's mainly because they're so used to dealing with polynomials. So if I said, what's the antiderivative of x to the negative 2 dx, which by the way is the integral of 1 over x squared dx. If I were to say, what's that integral? People know I would add 1 to the power and divide by that new power. And then I'd add a c at the end of it. So they properly say that's negative 1 over x plus c. So they get used to that idea of adding 1 to the power and dividing by the new power. And it is true, that works for all powers on x except for 1. The one power where that doesn't work is when you have 1 over x, or in other words, x to the negative first. And the reason why that doesn't work is if you added 1 to the power and divided by the new power, you'd be dividing by 0. That does not work. So the integral of 1 over x, the indefinite integral, is going to be the natural log of absolute value. Those absolute values are so important. The natural log of the absolute value of x, because the derivative of the natural log of the absolute value of x is 1 over x. Up to this point, you've probably only seen the derivative of the natural log of a regular old x, and that is also 1 over x. However, it is very important to remember that when this was introduced to you, at least if you've been watching my video series, when I introduced the derivative of the natural log, I then said, hey, by the way, it is very important to note, and it will be in the future very, very, very important, that actually it's the derivative of the natural log of the absolute value of x. That is actually equal to 1 over x. And so it is critically important that you remember, if I want to integrate 1 over x, its antiderivative is the natural log of the absolute value of x plus c. All right, so that's just an important, again, antiderivative or indefinite integral to remember. And then the very last one is that I think is super important, other than all the regulars, right? You should know the antiderivative or the indefinite integral, the sine, the cosine, secant squared, cosecant squared, all that stuff. But these are the kind of heavy hitters that people often forget. The indefinite integral of 1 over the square root of 1 minus x squared dx. That you would take the derivative of arcsine, or the sine inverse, to get that integrand. So therefore, the indefinite integral of this is going to be the sine inverse plus c. Don't forget the plus c. Very, very important. So there's no need for me to prove any of those, because you could just take the derivatives of the right hand side and showcase that they are the integrands. But it's also a very nice thing when you're evaluating indefinite integrals. You can always check your work by taking the derivative of your answer to see if it actually does turn into that integrand. So that does it for this video. In the next video, we'll actually use all this theory to jump into in evaluating indefinite integrals.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.